Okay, Assalamualaikum and hello, welcome back. So today we will continue with the new chapter, chapter 4, which is electrical machine. Okay, so this topic should cover only 2 weeks, but it is quite a lot. Okay, so most of the topic is a theory part. So bear in mind, you have to know everything. Okay, and so we start with the first part. Okay, you have two part. The first one is the DC machine and then the induction machine. You also get the book. Okay, the textbook here. Okay, the PDF is the textbook. This one is uh, the lecture note. Okay, so let me set this first. Okay, so we start with the first one, which is DC machine. So overview of DC, we will learn about the overview of the motor principle of the DC machine, rotating DC machine, shunt connection, and separately excited DC machine, DC motor, series connected DC motor, speed control, and DC generator. This one is cover a lot, so but we have to finish it up. So this is basically the image of the rotor. Okay. So at the end of this topic, you're able to select the proper motor types for various applications, state how torque varies with speed for various motor, and use the equivalent circuit for DC motor to compute electrical and mechanical quantities. Okay, so you have theories. Okay, this is theory. This is also a theory, and this one is the calculation. Okay, and you also have to understand the motor template data, understand the operation of characteristic of the shunt connected DC motor, series connected DC motor, and universal motor. So what is DC electrical machine? Okay, so electrical machine is basically your conversion of electrical system into mechanical system, which is this is motor, and if you flow it another way around, it is a generator. Okay, and electrical machine is link between the electrical system and mechanical system. So this one I already explained. Okay, so electrical machine can be divided into DC machine and AC machine. Okay, direct current or alternating current. And AC machine can be divided into two, whether it is a synchronized machine or induction machine. Okay, so you need to know the division of the electrical machine. Okay, and then this one, magnetic couple. Okay, two electromagnetic phenomena in the electrical machine. When the conductor move in the electrical field, voltage is induced in the conductor. This one is generator. When a current carrying conductor is placed in the magnetic field, the conductor experiences a mechanical force. This one is a motor. So this is the effect that we use to create a motor or generator. Okay, an electrical motor consists of a stationary part and a rotor. So you have a stationary part, stator, okay, and then a rotor, which is the rotating part. Okay, so understand this, Okay, the one that is not rotating is a stator, and the one that is rotated, it is called rotor. Okay, combination of this will become motor or generator. Okay, rotor is connected to the shaft that coupled with the mechanical machine to a mechanical load. The shaft and the rotor are not supported by bearing, so that they can rotate freely, as illustrated here. So you can see here, this is a stator not moving. You have shaft here. This is the rotor. Okay, this is the end housing. Okay, so make sure you know the difference between the stator and the rotor. Okay, rotor rotates. Okay, stator static. Depending on the type of the machine, either the stator or rotor or both can contain current carrying conductor configured into coil. Okay, so basically depend on the design. Okay, some of it can carry current, okay, into the coil. Slot cuts into the stator and rotor to contain the winding and the insulation. current in the winding set up a magnetic field and interact with the produced torque. Okay, so for this case, you need to know what is the slot. So this is a slot, empty space. Okay, empty space, and empty space. This is rotor, this is stator. So your winding is here. You wind between the slot. Okay, you wind between the slot and it can carry current. Okay, so make sure you know what is slot. Okay, so the current will produce the torque needed. Okay, so usually the stator and the rotor are made of iron to intensify the magnetic field. Okay, as in the transformer, if the magnetic field alternated in direction through the iron with the time, the iron must be laminated to avoid large power losses due to eddy current. So basically it say that the stator and rotor is made from iron and it is laminated to avoid eddy current. Refer back to your previous chapter. Okay, the transformer chapter. Okay, so this is a characteristic of electrical motor. Okay, you can have a AC motor, remember AC, and you have DC. So AC motor you can either have 3-phase or single phase. So you can either have a induction motor or synchronized motor. Okay, for induction machine you need to know that you can either have a squirrel cage and wound field. Okay, this is the standard one. Okay, widely used, squirrel cage or wound field. Okay, for synchronized you can either a permanent magnet or DC field winding. Okay, make sure you know for this one, synchronized can either permanent magnet or DC winding. Okay, for the stator, of course this is for the rotor. The stator you have a 3-phase armature winding. Okay, okay, you need to know what is the command and the application. Okay, for squirrel cage, of course this is simple. Okay, very simple. Squirrel cage is basically just a metal, no winding at all. Okay, very common for fans and pumps. Okay, make sure you know the example and the advantages. Okay, wound field is adjustable speed using rotor resistance. Okay, it's suitable for hose and cranes. Okay, for synchronized motor permanent magnet, the advantage is you have a precise speed. Okay, okay, this one maybe you can use a transport sheet material. Okay, which need a precise speed. Okay, and then you may have a DC field winding. This one is for large constant load potential for power factor correction. This one is usually for what you call power factor correction. Okay, make sure you know the advantages and the application. And then you need to know there are also a single phase AC motor, which is induction or synchronized. For induction, of course, you only have a squirrel cage. Okay, and for the stator you have a main and auxiliary winding. Okay, this one I have several type. Okay, phase capacitor, starter, capacitor run, simple, and many more. This one. Okay, try to look at it. Okay, synchronized, for single phase you have a low torque, fixed speed. Okay, this one is for timing application. Okay, then for DC motor you can either have a wound field or permanent magnet. Okay, wound field is basically you have to supply the current, okay, to create a magnetic field. Permanent magnet is basically you have a magnet. Okay, same as here. Okay, this one permanent magnet means that you have a naturally occur magnet. Okay, don't need any additional current. Okay, so you have, where is it? Okay, wound and permanent magnet. So for wound you have 3 types, either shunt connection, okay, series connection, or compound connection, which is combination. Okay, this one for rotor it is armature winding, and then for the stator you have a field winding. So armature winding is the winding at the rotor. Field winding is just to create what it calls a magnetic field. Okay, make sure you know the application. Okay, industrial application, grinding machine, or hoist. Okay, series connection is for the high torque, low speed. Okay, okay, and it is very dangerous if not loaded. Okay, usually for drill, automatic starting motor, Okay, so this one is for car starter, okay, or motor starter. We use a series connected wound field DC motor. Okay, and compound connection can be designed to tailor the torque speed characteristic. So basically, it designed for suitable torque speed characteristic. And then you have a permanent magnet. This one usually for the servo motor. Servo motor is basically the motor usually in use in the robot. It can adjust it according to the angle. Okay, machine tools. Okay, computer peripheral and automotive fans, windows, motor. Okay, so make sure you know this. Okay. Okay, we continue with the armature and field winding. Okay, the primary purpose of the field winding is to set up the magnetic field of the machine. Okay, field winding is basically just to create a magnetic field. Okay, so the current in the field winding is independent of the mechanical load imposed to the motor, except in the series connected motor. Okay, so basically it says that the mechanical loads, okay, and the field winding is independent except for the series the series connected. On the other hand, the armature winding carry out the current that depend on the mechanical power produced. Okay, so armature current field, okay, armature current is related to the load. Field usually not if related to the load, but field except for the series. Okay, series type. On the other hand, the armature winding carry, okay, this one, okay, typically the armature current amplitude is small when the load is light and larger when the load is heavy. So for armature current, the larger the load, the higher the current. If the machine acts as generator, the electrical power output is taken from the armature. In some machine, the field is produced by the permanent magnet, and the field winding is not needed. Okay, so if you use permanent magnet, okay, you don't need a field winding. So because field winding is just to create a magnetic field. Okay, so next is, okay, so you can see here table 16.1 shows the location of the stator or rotor of the field and armature winding for some common type of machine. For example, in a three-phase, okay, AC machine, the field winding on the rotor and the armature is on the stator. In the other machines such as wound field, location are reversed. Okay, this one is not provided. Okay, so basically it states that, okay, you can see here armature and field winding. Okay, they can either at the stator of the rotor or the stator of rotor. Okay, so this one can be at the stator, can be at rotor, and sometimes this one can be at stator and can be at rotor depending on the machine. Okay, this is what it says. Okay, next is the DC motor. DC motor are those that are provided by the DC source. Okay, one of the difficulty with the DC motor is that it is nearly all electrical energy is distributed as AC. Okay, if only AC power is available and we need to use a DC motor, a rectifier or some kind of converter is used to convert AC to DC. So for example, for DC motor, you have to use DC. But if you have a source of AC, you have to rectify. Okay, rectify means you convert AC power supply to DC power supply. So you need to use a rectifier. Okay, that's why usually AC machine is preferable. Okay. Okay, exceptions are automotive application in which DC are readily available from the battery. Okay, this one automotive is the car. Okay, even if your car is the combustible engine, ICU, I think it's called internal combustion engine, ICE. Okay, so you need to use a DC motor to start your ICE motor. Okay, so usually DC motor is used because of the battery. Okay, Sometimes the windshield, wiper, and everything inside the car also start by using a DC. Okay. In the most common types of DC motor, the direction of the current in the armature conductors on the rotor is reversed periodically during rotation. This is accomplished with a mechanical switch composed of brushes mounted on the stator and the commutator on the mounted shaft. Okay, there is no picture. Okay, let me search for picture first. So you can see here, this is commutator, this is brushes, this is magnet. So magnet will produce a magnetic field, and this is the winding. Okay, so brushes, okay, you can see here positive and negative. Okay, if you keep supply at the same direction, it's just stop, because after this point it will reverse back. Okay, so that's why we use a brush. This is brush, this is commutator. Okay, to flip the direction of the current, so it will keep rotating. Okay, that is meant by this sentence. Okay, the limitation of the DC motor is that the brushes and commutator are subject to wear, and a significant disadvantage of DC motor is relative to frequent needs of maintenance. So remember that I show you this one, the brush and the commutator. Okay, this one is keep spinning, so it will be wear and tear. So DC motor needs to be maintained frequently. So that is limitation of DC motor. Until recently, an important advantage of a DC motor was their speed and direction could be controlled more readily than those of AC motor. Okay, this is the advantage of DC motor, because you can control the speed and the direction easily. However, this advantage is rapidly disappear because of the electronic system that can be very frequency of AC source become economically advantageous. Okay, so previously, if you want the speed and direction control more easily, you use a DC. Okay, but right now power electronics has advanced. Okay, so power electronic can vary the frequency of a AC source easily. So you can use the AC. Okay, you can have the DC motor advantages in an AC. So that is mean by this. Okay, this variable frequency source can be used with a simple rock AC induction motor to achieve speed control. Okay, you can see here advantage of the induction motor, it is rock. Okay, hard to destroy. Okay, very rugged. Okay, and you can use a power electronic. Okay, power electronic to control the speed. So let us look at the electrical machine basic structure. Okay, so you can see here, this is the structure, this is stator, this inside here is rotor, this is the air gap. Okay, this one is air gap. Okay, this is the winding, A and A bar, B and B bar, C and C bar. This one is the three-phase. Okay, three-phase AC system. Okay, so this is the winding also inside internally. Okay, you can see here. Okay, so basic the structure of an electrical machine has two major components, which is stator and rotor. Stator static, rotor rotating, separate by the air gap. This is the air gap I showed before. Okay, stator doesn't move and normally in the outer frame. Okay, rotor is freely move inner frame. Okay, so it looks something like this. Okay, so this is the construction. You can see here, this is fan. Okay, fan is to cool down the machine. Okay, okay, this become very hot, so you have to add fan. Okay, this is the poles. Okay, this is the poles, is basically where you put the winding, so we call it poles. Okay, so this is brushes. Okay, bearing, rotor winding, commutator. I think this one is DC machine. Okay, yes, this is DC machine because you have a commutator and brushes. Okay, direct current machine fundamental. Generation action. An EMF voltage is induced in the conductor if they move through a magnetic field. Okay, So remember, if the magnetic theory, okay, before, okay, if you have a voltage, okay, and EMF voltage is induced in the conductor if moved through magnetic field. Okay, for motor, a force of inductor is in the conductor that has current carrying will place a magnetic field. Okay, force will produce, for generator EMF will produce. Any DC machine can either act as generator or motor. So if you have a DC machine, okay, if you apply voltage at the terminal, it will become motor. But if you rotate the motor, it will become generator. Okay, so this is mean by this sentence. You can interchange for DC machine can be either generator or motor. Okay, and this one is not applied for AC. The AC is different. Okay, this is the DC machine construction. Okay, of course you have stator, you have rotor. Okay, you can see here, this is the field winding. Okay, this is the field winding at the stator. Okay, this one is the armature winding at the rotor. Okay, so you can see here the green one. Okay, the current goes to here. Okay, this is brush. Okay, brush, and you have a commutator here. Okay, and this is the stator part with poles. This one is to generate the magnetic field. Okay, this is a field winding. Okay, just to create a magnetic field. Okay, you can see here the stationary part of the machine carry out the field winding to produce the required magnetic field by the DC excitation. So you apply DC here, it will create a magnetic field, no stop. Okay, so the rotor, okay, is the rotating part of the machine. Rotor will carry out the distribute winding, and it is winding where the EMF is induced. Okay, this one is armature winding. Make sure you differentiate between the field winding and the armature winding. Okay, this is for DC. Okay, remember what I said before? We focus on the DC part first. Okay, at the beginning we focus on what is available, and then we focus on the DC. So if you want to look at the real stator and rotor, you can see here, this is the field winding. Okay, and this is the pole. Okay, this is the motor house. Okay, so this is the rotor of the DC. Okay, this is the stator. Okay, and this is the rotor. So you can see here the rotor. Okay, this is the winding, armature winding. Okay, this is bearing, ball bearing. Okay, and this is the commutator. Okay, brushes should be here. Okay, it's not sure. Okay, this is the iron core, this is the coil. Okay, so basically this is the rotor of the DC. So this is the commutator. Okay, you can see here insulated between the segment, so it doesn't short. Okay, for this one you can see here the wire is near to each other, but it's not short because it is laminated. Okay, laminated means that the wire is basically have insulation. It's not a bare wire. This one is bare wire, this is not. Okay, so this is the flow of power flow. Okay, for the three-phase electrical source into induction machine load and some power loss around. Okay, I think the notes is quite not organized properly. Okay, so just look at here. So you can see here, this one is AC actually. I think it's AC. Okay, so make sure you know this one. Okay, this is the power. Okay, so you have electrical loss. Okay, you have input power and this is output power. Okay, do you have electrical loss and mechanical loss? Okay, so make sure you know this figure. Okay, you need to know this figure. So you have an input power, you have a copper loss, eddy current loss, hysteresis loss. This is in the form of electrical loss. And then you have a friction loss, and you have a windage loss. So this one is in the form of mechanical loss. Okay, I think most of you know all of these loss. Frictional, of course, you know. Windage is the resistance with because of the air. Okay, windage loss. Okay, losses, power rating, and efficiency. Okay, when it comes to motor, you need to know this. Okay. Okay, input power is equal to square root of 3 Vrms Irms cos theta. So remember, this is formula if you use the line voltage and line current. Okay, square root 3, and this is for 3-phase. Okay, so mechanical output power is P is equals to T torque multiplied by this one. Okay, angular speed. Okay, so this one I think you already learned about is in physics. P out is equal to T out Wm. Okay, angular speed and the torque. Okay, so this is the P in, this is the P out. Okay, power rating of the motor is the output power of the motor that can safely produce continuous basis. Okay, when you buy a motor, they will usually give a power rating. Okay, power rating is just the operation, the supposed operation of the motor. So basically, power rating is the output power. So this one, we don't look at the input, we look at the output. Okay, remember, input and output. Output is much more smaller, input is much more larger because it accommodates the losses. So when it comes to power rating, you look at the output. Okay. Okay, for example, we can safely operate an 5 horsepower motor with a load that absorbs 5 horsepower of mechanical power. If the power is required by the load is reduced, the motor draws less input power from the electrical source. Okay, and in this case of the induction machine, speed up slightly. Okay, so this one is about DC. Is about IC. Okay, for induction motor, like I said before, induction motor is not good in speed control. Okay, why? Because if you change the load, if you reduce the load, the speed increase. Okay, so this is important. It is important to realize that the most motor can be supply output power varying from 0 to several times of the rated power depending on the mechanical load. Okay, it is up to the system designer to ensure that the motor is not overloaded. Okay, so basically it says that even if the rated is somewhere here, you can connect to the mechanical load much more higher. Okay, but make sure it's not too overload. Okay, the chief output power limiters of the motor is the temperature rise due to the losses. Okay, so the higher the load, the higher the loss. Okay, and the higher the temperature, it will damage the motor. Okay, thus the brief overload does not cause significant rise to the temperature. Okay, if you have a overload for a small time, okay, short time, okay, the rise of the temperature is acceptable, but if long time is not very good. Okay, this one is the efficiency. Of course, you can calculate the efficiency, the output power divided by the input power. This is a standard efficiency equation. A well-designed electrical motor operates closely to the rated capacity, have efficiency at a range of 85 to 95%. On the other hand, if the motor is called upon to produce only small fraction of its power rated, the efficiency is lower. Okay, this is why when you want to buy a motor, make sure you buy it according to your need. Okay, if your output power is 5 horsepower, you have to buy 5 horsepower. If you operate lower than that, it will not be efficient. Okay, there are a lot of losses. Okay, this one is the speed regulation. Depending on the torque speed characteristic, the motor may be slowed down as the torque demand by the load increase. Okay, so speed regulation is defined as the difference between the no load speed and the full load speed. Okay, So this is the speed regulation. So no load minus full load. No load, which is much more faster. Okay, this one is slower. Full load means that the load is at the full capacity. Okay, make sure you understand what it means by full load. Okay, for example, 5 horsepower. Okay, if the motor is rated as the 5 horsepower, full load means that the load is 5 horsepower. Okay, something like that. Okay, no load speed minus full load speed divided by full load speed. This is the speed regulation. Okay, the smaller the number, the better the motor. Okay, and then you need to know what is the principle of DC machine. Okay, idealized linear machine shown in figure 16.6. A DC voltage DC voltage source VT is connected through a resistor RA and switch closed at T equals to 0 to a pair of conduction rail. A conduction slide without any friction. Assume that the rail bar will have a zero resistance. Okay, so this is a idealized linear machine. Okay, so you can see here, this is the RT. Okay, you have RA, okay, to control the current. Okay, and then you have a magnetic field. So X means that goes into the paper. Okay, and this is the sliding bar. Okay, it can move without any friction. Okay, so you can see here, if you connect this one has the connection. This one is conductor, so it will complete the circuit and the current will flow to this. Okay, flow something like this. Okay, so force will be created. Okay, so this sliding bar will move. If not mistaken, it is right hand side. Okay, so the current will move down. Okay, so if not mistaken, it will move this direction. Okay, you have to use right hand rule. Okay, a magnetic field is directed into the page perpendicular to the plane and the rail. Suppose that the bar is stationary at the switch T is equal to 0, and just after the switch is closed, the initial current give that A. Okay, so current is just VT divided by RA. So voltage divided by R, you get the current. This is zero resistance. It's just a conductor. Okay, flow to the clockwise. Okay, this one flow something like this, and then round the circuit. Okay, a force given by F is equals to I length multiplied by B is exerted on the bar. Okay, the direction of the current is and I is towards the bottom of the page. Thus the force directed to the right. Okay, so means that the direction is goes here. Okay, to the right. Okay. Okay, when the bar accelerated to the right, as the bar gain velocity, it will cut through a magnetic field line. A voltage will be induced at the bar. Okay, the voltage is the positive to the top at the end of the bar. Okay, so this one E, B, L, U. Okay, so when you apply force here, okay, when you apply the voltage here, it will produce a current something like this. Okay, this sliding bar will move to the right. Okay, and remember, when you move some wire, okay, move wire against the magnetic field, it will create a positive and negative magnetomotive force. Okay, so at the same time, this one become something like a voltage source. Okay, plus minus. Okay, so this is means by this one. Okay, so as a result, you can say that it's something like this. Okay, you have a VT, RA, okay, the switch, and the EA, BL, V. Okay, so basically the moving wire, okay, the moving motor or rotor will become something like a voltage source. Okay, this is basic principle of the DC motor. Okay, So equivalent circuit for the system as shown in figure 60.7. Notice that induced voltage EA opposed to the source VT. So you can say that the IA will equals to, okay, you can do the Kirchhoff voltage law here, is something like this: VT minus EA divided by RA. Okay. Okay, the velocity of the bar builds up, the energy is absorbed by the induction motor, the induced voltage, and the energy show up at the kinetic energy of a bar. Eventually, the bar speed up become high enough that EA is equals to VT. Okay, so what it means that the faster it goes, okay, BLU, remember BLU, U is the speed. Okay, so if the faster it goes, the higher the voltage, the EA, okay, the induced voltage. At the end, the EA will be equals to VT. Okay, so then the current and the force become 0. Okay, so and the bar goes at a constant velocity. Okay, at the beginning it will increase, the current will start very high, but at the end the velocity constant. Okay. Okay, we continue with the operation as a motor for DC machine. So now suppose that the machine on, okay, now suppose that the machine load exerted on a force to the left is connected to the moving bar. Okay, then the bar is slowly down slightly, resulting in the reduction of the induced voltage. Current flow to the clockwise in the circuit, resulting in a magnetic induced force directly to the right. Eventually, the bar slowly slow just enough so that the force created by the magnetic force F is equals to IALB equals to the load force. Okay, then the system move at a constant velocity. So okay, so basically okay, where is it? Okay, so basically if you have a load, okay, so if you have a load, so EA will not equals to this one. Okay, it should be lower. Okay, so this is the operation of the motor. Okay, F is equals to IALB. Okay, then the system move constant velocity. Okay, in the saturation, power delivered by the source VT is converted partially to heat and in the RA, okay, and then partially to mechanical power. It is absorbed by the EAIA. Okay, so basically the power here, this is the power loss in form of heat, and then the energy here is just EAIA. Okay, so YA is amateur, amateur. So this is amateur winding. Okay. Okay, so you have a power. Okay, mechanical power will become EAIA. Delivered the induced voltage that is shown as mechanical power. P equals to FU. Okay, frequency. Okay, so I forget the name. So basically EA, the induced voltage, will show up as a mechanical power. Okay, and if it is operated as generator, suppose that the bar moving at a constant velocity such as EA is equals to VT and the current is 0. Okay, then if the force is applied, the pulling bar even faster towards the right, the bar speed up, the induced voltage EA exceed the voltage VT. Okay, and the current circulate in the counterclockwise. Illustrate and figure this one. Okay, so if you move, EA is equals to BLU. Okay, so U is the speed, you increase the U, you increase the EA. Okay, and Of course, the current will flow here if the Vt is much more larger. EA is much more larger than Vt. IA will circulate as a counterclockwise. Okay, so because of the current has reverse direction, the force induced in the bar by the field is also reverse and the point to the left. Okay, so eventually the bar speed up stabilized with the pulling force equals to the induced force. Okay, the induced voltage delivered power EAIA partly resistant to the PRRAIA squared, okay, and partially to the battery PT is equal to VT IT. Okay, so when you deliver this, some power lost to here and some power goes to the VT. Okay, so the current circulate counterclockwise as illustrated because of the current has reverse direction. Okay, this one already okay. Thus, the mechanical converted into electrical energy eventually show up as losses in the resistance or stored in the chemical in the battery. So energy stored in the battery and losses here. Okay. The basic principle of the rotating DC machine are the same for those who are linear DC machine. The most common type of DC machine contains a cylindrical stator with an even number of P of magnetic poles that establish field winding by the permanent magnet. Okay, the poles are alternating between north and south around the peripheral of the stator. So how can I show this? Okay, if you have a you have a pole here. Okay, you have north south. It is alternating. Okay, so inside the stator is a rotor consists of laminated iron cylinder mounted to the shaft and supported by the bearing so that it can be rotated. Slot cut lengthwise into the surface of the rotor contain the armature winding. A rotor with the armature conductor is rated at the figure 16.9. Okay, this one I think I already show you. Okay, armature conductor slot on the rotor. So you have a winding here. It will place here. Okay. Okay, a cross section of the two poles machine show in the flux line in the air gap is rated in the figure 16.10. So you can see here. So this is the field winding. Okay. So you have into here, this is out. So this become north, this become south. Okay. So this is the armature conductor. Okay. So magnetic field tend to take apart at least reluctant because of the reluctance of the air is much more higher than the iron. The flux takes the shortest path from the stator to the rotor. Okay, thus the flux in the air gap is perpendicular to the surface of the rotor and the armature and conductor. So this is basically the movement of the flux. Okay, goes in, go here, and then this one here. Okay, furthermore, the flux density is near constant at the magnetic over the surface of each pole. Between the pole, the gap flux density is small in magnitude. Okay, in the motor, external circuit source provided the current at the field winding and the armature conductor. So basically, if you have an external source, it supply for this one the field winding and the armature winding. Okay, the current direction shown in figure 10 result in a counterclockwise torque. This can be verified by applying equation F is equals to IL B. If the force is on the current carrying conductor. Okay, another thing you need to know is that the term pole. Okay, so this is the cross section of the 4-pole machine shown in figure 1611. So you can see here you have 4 poles. So 1, 2, 3, 4. Okay, 4-pole or 2-pole pair. Okay, So make sure you know what is pole. So this has 4 pole. Okay, or pole pair. Make sure you know the difference. 4 pole is equals to 2 pole pair. So 1 pole pair, 2 pole pair. Okay, notice that the direction of the current in the armature must be reversed under the south pole relative to the direction of the north pole to aid the contribution of the total torque. So you can see here, okay, at north you have current goes into the paper, okay, and at the south it will go out to the paper. Okay, so this is the armature current move like this because you want to aid the total torque produced. Okay. Okay, next is the induced EMF and the commutation. As the rotor turns, the conductor moves through the magnetic field produced by the stator. Under the pole phase, the conductors, the field, and the direction of the motion are mutually perpendicular, just as the linear machine discussed in the slide principle of the DC machine. Thus, a nearly constant voltage is induced in each conductor and is just moved under a pole. However, the conductor moves between poles, the field direction reverse. Okay. So therefore, the induced voltage falls to 0 and build up with the opposite polarity. Okay. A mechanical switch known as a commutator reverses the connection to the conductor as they move between poles so that the polarity of the induced voltage streams from the external machine is constant. Okay, let us illustrate this point with a two-pole machine containing one armature core as shown in figure 12. In this case, the end of the core are attached to the two-segment commutator mounted to the shaft. The segments are insulated from one another from the shaft. Brushes mounted to the stator makes the electrical contact with the commutator segment. Okay, so this is the illustration. Maybe this one is much more easy to understand. So you can see here, so you have B from north to south, magnetic field from north to south. This is the commutator. Okay, this ring is the commutator. This is positive, this is negative. Okay, so when it positive negative, it will move here. Okay, so you can see here VT is positive. Okay, positive VT, and then at this separation of commutator, the voltage drop. Okay, VT is not equals to this one. This one is disconnected. Okay, between brushes and commutator there is no connection, so the circuit is not complete. So voltage drop. But after the rotation complete, you will get the same this one, but now is connected again in the different direction. So you can see here, this is VT is equals to VAD, and then VT is equals to V negative VAD. It is in the reverse direction. Okay, so you can see here the magnetic field is still constant, but the direction is different, so it will make sure that the direction of the rotation will kept constant. So you can use a left hand rule. Okay, so you can see here north to south. Okay, and positive, the current goes here. Okay, and then you have the force goes up. Okay, this one force goes up. So for this case, the current move from here to here. Okay, the current, okay, the force goes down. Okay, same as here, you can apply. You can see here the direction of the torque is kept constant. Okay, sorry, I use left hand rule. Okay, okay, notice that the rotor turns in figure 12. The left hand brush is connected to the conductor under the south pole, and the right brushes connected to the conductor under the north pole. Okay, so this one is means. Okay, left at the south, okay, right at the north. Okay, the voltage VAD induced across the terminal of the coil is an AC voltage as shown in figure. This voltage passes through the zero when the conductors are between poles. While the conductors are under the pole face, the flux density is constant. Okay, so while the conductors are under the pole face, where the flux density is constant, the induced voltage has nearly constant magnitude. Okay, because the commutator reverse the external connection to the coil as it rotates, the voltage seems to have external terminator of the constant polarity. Okay, notice that the brushes short the armature winding briefly during the switch process. This occurs because of the brush are wider than the insulator between the commutator segment. This shorting is not a problem provided that the voltage is small when this occurs. Okay, the machine have various provision to ensure that the coil voltage is close to zero during commutation for all operating conditions. Okay, commutator in the typical machine contain 20 to 50 segments. Because only the part of the coil that are commutated at the time of the terminal VT of the real machine show relatively little fluctuation compared to the two segments. Example we use to illustrate in this concept. The terminal voltage is actually in this one. Okay, so you can see here the voltage, although the commutator is disconnected a little bit, so this is only slightly change. Okay, it's less pronounced as shown here. Okay, generally the commutator segment are copper bar insulated from one another from the shaft. The brushes contain the graphite so that lubricate the sliding contact. Even so, a significant disadvantage of DC machine is that it needs to replace the brushes and redress the commutator surface because of the mechanical wear. So this is the limitation of the commutator. Okay, it will wear off. Actual armature consists of a large number of conductors placed around the circumference of the rotor. To attain high terminal voltage, many conductors are placed in series forming coil. Furthermore, there are usually several parallel current paths through the armature. Okay, so the armature conductor and the connection to the commutator are configured so that the current flow to the opposite direction on the south stator pole and the on the north stator pole. Okay, as mentioned earlier, this is necessary so that the force on the conductor produces at the top. The construction details are produced. These conditions are beyond the scope of our discussion. As user electrical motor, you will find the external behavior of the machine helpful more in the detail of the internal design. So this sentence, where is it? Okay, not too much picture, quite hard to explain to you. Okay, wait. Okay, the explanation just show that you can see here, this is the rotor. Okay, this is the commutator. You can see here, this is the commutator. Okay, the brush will goes to the wire here. Okay, and this is the gap that the sentence mentioned. Okay, this gap is much more larger than the brushes. Okay, try to imagine what is the brushes. Okay, so you can see here the commutator is many. Okay, where is it? Okay, this one. Okay, commutator segment, you have 20 to 50 segment. Okay, it's not only two. Okay, there are a lot. Okay, that's it for today. Okay, we will continue tomorrow. Okay, with the equivalent circuit of DC motor. So this is the more towards the calculation. And don't forget, today is considered as 10 January, and at 9 PM today, okay, 9 PM at night, there will be test 1. Probably there will be test 1. Make sure you check the Telegram for updates, but make sure you attend the test 2. Okay, and don't forget to slide in your attendance. That's it.